Big round of applause.
Right. Yes. All right. Cool. Thank you so much for the introduction. So indeed, I mean, the scheduling is just spot on, I think. So if you've been to Benedict's talk, we're going to continue in this vein and talk about this paper Mova that we published with Nick, Albert, and Ilya at Nethermind Research, which improves on this Nova folding scheme in a way that eliminates like critically expensive steps, which we're going to look at, and also avoids these sumcheck operations that appear in Hypernova. Okay, so just going back to the basics a bit here, even though Benedict introduced some of them. We are talking about relations here. Relations are just subsets of bit strings. And the pairs in this relation are called instance witness pairs, in the sense that we say that W is a witness for X. And as we've seen, for example, in Giacomo's talk, we have a number of protocols that we call snarks for these NP relations. So those are the relations where you can check that a witness corresponds to an instance in polynomial time. And you have a number of protocols that exist today, for example, starks, that allow a prover to convince a verifier that it knows somehow the corresponding witness for an instance. Folding, I think Benedict didn't say that, but you can think about it as some sort of pre-processing for snarks, in the sense that you have a lot of instance witness pairs. You want to show that they are in the relation. You could just throw a snark at each of them. But you can also kind of compress them into a single pair and then show that they are in the corresponding relation at the end. And in this sense, folding is like some sort of pre-processing where you have a lot of instance witnesses, you combine them, then you throw a snark at them. So today, and because we're thinking about the Nova system in particular, the NP relation that we're interested in is the R1CS relation. So it was introduced before, but I'm just going over it again. So you fix some matrices, some square matrices, which have size m and at least m non-zero entries. The R1CS relation essentially says, I know a witness, such that if you give me some public inputs x, and I build this vector as x1 and my witness, then this relation holds. So this is the multiplication of a times z, and then you take the component-wise product or Adama product with bz, and then this should be equal to cz for the matrices abc that we've introduced. And this is a bit kind of a modification of the R1CS relation where we commit to the witness. So in the instance, you also have a commitment to the witness. So that's the relation we're talking about. So folding schemes, which were also called accumulation schemes in the previous talk. So they're just an interactive protocol between a prover and a verifier, such that you start with two instance witness pairs in two relations, say R and R accumulated, and V only knows the instances. Then they interact in some way, and in the end they output a new instance, and V additionally outputs a new witness. And now you want to have like some basic security properties, which are completeness and knowledge soundness. So it is, if you follow the protocol honestly, then the instance witness pair you get in the end must be in the relation. That sounds reasonable. And then conversely, if the instance witness pair is in the accumulated relation in the end, you can run an efficient algorithm, which is going to extract witnesses for these instances such that the pairs are in the relations. So this is what we call folding scheme, and R to R accumulated folding scheme. And as Benedict said, the idea is that if you can make this process efficient, simple, or it's like very lightweight, then instead of just throwing a snark at each of the instance witness pairs in the relation, you can combine them into a single relation and prove the membership to a single relation. So this is the idea behind folding schemes. You have a computationally intensive process, which is like just using the snark to prove that something is in a relation, and then you have this combination process that you can run first, so that you reduce membership of like a whole bunch of instance witness pairs to the membership problem of a single instance witness pair belonging to this accumulated relation. So, as Benedict said, also one of the most common ways to build a folding scheme is by just taking random linear combinations. You take the instances and the witnesses, you combine them using some random challenge from the verifier, and then you update the commitment homomorphically. So let's see a very simple example. Here, imagine the relation is not like this R1CS relation, it's just like multiplication with a matrix should give 0. So this is a very simple, idealized relation. So if I have two vectors, z1 and z2, such that az1 and az2 are 0, then one thing I can do is just take a random challenge alpha, define z as the random linear combination using alpha, and if my commitment scheme is additively homomorphic, I can update the commitment to z without computing it again, but simply by doing the linear combination on the commitments. And then, obviously, because the relation is linear, then az is also equal to 0. So in this way, I've reduced the two problems of showing that z1 and z2 equals 0 when multiplied by a to the problem of showing that z has this property. Okay, so that's the very simple idea. So what Nova does is it applies this idea to the R1CS relation, even though the condition is not exactly linear. And it's not linear because you get the Hadamard products, and these are component-wise, and so one thing that you can check for yourself maybe is that if you have two vectors z1 and z2 that satisfy the R1CS relation, and you try to take the linear combination, then unfortunately it does not hold. That the R1CS relation does not hold. Instead, you get some extra term, which is what we call an error term. And so these error terms are exactly what is needed to make some relaxed relation hold, which is this one. So you have the R1CS relation, but then you have some extra term that comes from the cross term when you multiply AZ and BZ when Z is the random linear combination. So Nova says, okay, we have these error terms, but it's fine, we can work with them. Let's just define a relation that is a bit larger, that incorporates these error terms, and let's build a folding scheme for that relation instead. So what you get is a folding scheme from the committed R1CS relation to this new relation, which is called the committed relaxed R1CS relation. So it's the same relation, except that here, the equation is not AZ times BZ equals CZ, it's AZ times CZ equals some scaling factor times CZ plus some error term. And you also need to commit to the error term in the instance. So very quickly, how does Nova does this? So I realized that there's a little typo. I'm sorry about this. This should be W1, this should be W2. But you have an instance in the committed R1CS relation, and you have an instance with witness pair in the committed relaxed R1CS relation. You want to fold them. So how does Nova does this? So first they compute this cross term. This is the term that appears when you do the product, and you get this kind of extra term. This is the term you get. The prover needs to send a commitment to it. Okay? Then the verifier sends the random challenge, and P and V update the relevant quantities by taking random linear combination. So this is just like the same idea that we had before, but just applied to this new relation. So now if you look at this, this, for example, is just a few field operations, because these are field elements. This here is just like a bunch of group operations. You're just taking like a multiplication by a scalar times a group element plus another group element. So this is like essentially very lightweight. But the first point is actually the problem, because you see this vector t, you need to commit to it. And now if you've like ever seen like additively homomorphic commitments, you know that many times they are curve-based. And so when you try to commit to this cross term, it's essentially a multiscalar multiplication over the group defined by this curve. And moreover, and that's the kind of important point, the elements in the cross term are arbitrarily large. Like they can be arbitrary field elements because you're taking arbitrary linear combinations. If you've read the Lasso paper, you know that they've made like a really critical point about the fact that when you have arbitrarily sized field elements, committing to them by using like some sort of exponentiation can be very, very expensive. So in the majority of practical scenarios, this is actually the bottleneck for Nova. So I guess the question is, can we avoid it? Can we avoid committing to the cross term? So as Benedict mentioned, there are schemes that do this. There's Hypernova. So Hypernova is actually for CCS, but you can specialize it to R1CS, and it commits to no error terms. However, it uses the sumcheck protocol in the folding step. And the sumcheck protocol has log m rounds, where m is the size of the witness. So, as Benedict mentioned, when you're trying to use folding scheme in IBC, for example, you need to represent the verifier inside the computer. I mean, you need to represent the circuit of the verifier. So if you have log m rounds, if you have log m rounds, the verifier needs to do log m hashes. Sorry. Yeah. Yeah.
can also take a right here, sit down.
Sorry about this. Yeah, so I was saying, so the verifier needs to do log m hashes, and so when you represent it in a circuit,
You want to sit down for?
No, I'm okay. Yeah. You represent it in a circuit, and so you lose some efficiency. Then in Protostar, Benedict actually includes an optimization which eliminates the need to compute the majority of the commitments. So there is still a commitment to an error vector, and it increases the prover's group operation work, but essentially, yeah, okay, so that's it. It eliminates the majority of the commitments to the error terms, but there's still like this optimization which is pesky to do in practice, and you increase the prover group operation. So I guess an updated question can be, can you avoid the commitments to the cross terms altogether, and you can have O1 rounds? So that's the problem with Hypernova. You have log m rounds, and in Protostar you need to apply this optimization, which is, as I said, a bit pesky to do in practice. So the great news with Mova is that we answered this question with the affirmative, and the same answer was actually contained in an update to Proto Galaxy, so that we learned after the publication. But essentially you can see some version of Proto Galaxy as doing Mova, but it's expressed in a completely different language, and I think Nova really gives some new insights on the topic of Nova proving in general. So how do you fold relaxed R1CS in practice? So if you look at Nova, one first observation that I find quite surprising is the following. So if you look at the knowledge soundness proof of Nova, you never use the binding property of the commitment scheme to extract the error term. So I think that's quite surprising, because that means, why are you committing to the error term altogether? Like, if you never use the binding property of the commitment scheme to extract the error term, what is the commitment doing? You actually only use the fact that it's additively homomorphic. So intuitively what is happening is, once you have extracted the witness using the binding property, the error is actually determined, because you can just take AZ times BZ minus CZ. But so now think about it, like, you never use the binding property, but you use the additively homomorphic property. So why don't we just replace it by some general linear map? And we consider this new relation, committed relaxed R1CS, with this linear map. Well then, actually, if you look at the knowledge soundness proof, it just follows through. Okay, so that's, I think, a bit surprising. And now, sorry for the kind of little wacky example, but think about taking the linear map, which is just identically zero. and this is linear. The proof follows through. But now we're not committing to any. I mean, we're losing all the information about the error term. So what are the error terms even doing in this case? I mean, you can think about it as saying that the committed relaxed R1CS relation is really like kind of nonsense, or at least it's kind of degenerate. It says that, of course, there always exists an error term. Just take your witness, compute AZ, PZ, subtract CZ, and then you get the error term. So there always exists an error term. So actually, when you're folding committed relaxed R1CS instance witness pairs, the errors are superfluous. So you can consider this relation, and now you say, okay, but what happens when I want to fold like committed R1CS? Well, then unfortunately, it does not work. It does not work because you cannot ensure that the error is actually truly zero when you do the knowledge soundness proof. You can only ensure, like, you lose all the information, so you cannot say that the error is zero. So you need something more. But this actually gives us kind of a blueprint to build the folding scheme that we want. And the blueprint is you choose a suitable linear function from vectors with elements in F to some group. And suitable, I mean that it has at least enough information for you to do the knowledge soundness proof, so that you can ensure that the error is actually zero and not some nonsense. Preferably, it should be much more efficient than committing to the error vector, which is what we wanted to avoid in the first place. Then you build what is called a reduction of knowledge from committed R1CS to committed relaxed R1CS, which is just saying, I want to take an instance witness pair in committed R1CS and extend it to be in committed relaxed R1CS. And I want to do this in a knowledge sound way. And then you just build a folding scheme for this new relation, this new extended relation. So if you do these three things, you obtain a folding scheme for the relations that you want, where you never compute the error terms. You just compute the linear maps. So let's just go like point by point. We need to choose a suitable additively homomorphic function. So it turns out that a good choice is actually to choose the linear function that evaluates the multilinear extension of the vector at a random point. And actually this is useful for a variety of reasons. I'm going to try to kind of give you an idea of why it's the useful function in this case. And just recalling that for a vector with m elements in a field, the multilinear extension is the unique multilinear polynomial in log m variables, such that if you take any bit string of length log m, and if you evaluate this multilinear polynomial at this entry, then you get exactly the entry in the vector indexed by these binary strings. So you just take the integer that this binary string represents, and you take this entry in the vector. This is actually quite a classic way of representing vectors as some sort of polynomial. And if you give me all the entries of the vector, I can actually compute the evaluation of the MLE at any random point in a very small number of field multiplications. So here I wrote 3m is actually more like 2m. But the idea is like it's super efficient to compute the evaluation at a random point by doing some sort of interpolation. And this is one of the reasons why the MLE is so useful. So if you think about computing the commitment is an MSM size length. Here I'm saying that computing the MLE at R is 3m multiplications. So it's like orders of magnitude more efficient to compute this. Okay, so now we need to build a reduction of knowledge from committed R1CS to committed relaxed R1CS. Okay, so say the prover has an instance in R1CS, which means that AZ times BZ is equal to CZ. We make the verifier choose some random point, and the prover and verifier set the MLE at R to be 0. The prover outputs the witness. This is just like a very simple trivial scheme, and we just say that the MLE at R is 0, so that we are now in the committed relaxed R1CS relation. And I'm not going to go too much into the detail, but the knowledge soundness proof of this is actually surprisingly tricky. And I want to kind of bring the attention to this point, because I think it's kind of forgotten, but it actually always happens when you have a proof involving multilinear polynomials. So I think to anyone that's worked with multilinear polynomials, it's actually quite kind of clear that the proof should follow from Schwarz-Zippel. Schwarz-Zippel is this lemma that says that the multilinear polynomial cannot have too many zeros. But actually, if you try to do this, so a good idea would be, for example, we'll take a tree of transcripts for this interaction, and at each time you get a random point where the error is 0. So you say, okay, well, I just take enough transcripts, and then I deduce that the error must be 0 identically. But if you do this, you actually need more trees than you can afford. Like the tree needs to have at least like super polynomially many leaves, and you're restricted to polynomially many leaves. So you cannot do it. So then you say, okay, let's just run, for example, the extractor. The extractor runs the interaction once, and it outputs the error vector, and then we actually maybe can say, okay, since the verifier chose the challenge point at random, then we can use Schwarz-Zippel in kind of a probabilistic way. But you cannot do that either, because the random point was chosen before you extract the error. And so you cannot actually claim that they are independent. Sorry. Does that make sense? You cannot actually claim that they're independent, and so you cannot use the probabilistic way. And so you end up trying to kind of run the extractor 2 times, and you end up with something similar that's in the paper. But I just wanted to point out that when you're dealing with knowledge soundness proofs with multilinears, it's actually quite tricky. And then the last thing is like building this committed relaxed R1CS folding scheme with the MLE evaluation. And I'm not going to go too much into the detail here either, but you have a small subtlety that you need to deal with. It's that you don't have a single relation for the MLE evaluation. You have a whole family of relations that depend on the point where you evaluate. So you have, for example, for each choice of random point, you have a different relations which evaluates the MLE of the error at that point. And so we need to be able to efficiently reduce 2 evaluations of the MLEs of the error vectors at 2 different points to an evaluation of the MLE of the error vectors at the same point. And so here, a well-known method exists. It's called the point versus line. So the prover and verifier will define this linear function, which interpolates the random points. Then the prover will compose the MLEs with the line, and the new challenge point will be L beta for some beta chosen by the verifier. So this method exists. The problem is that the composition part is really expensive in general. Because you can imagine you need to, if you had like a random multilinear polynomial, you need to compose it at each of the variables with like a linear function. And this, like if the polynomial has no structure, I mean, who knows how expensive it is. But here again, I think it's the point where the MLE comes in clutch in some sense. And we show that the composition of an MLE of a vector with a linear function can be done in a very small number of multiplications. So this is like a second point where MLEs are crucial. And so overall, Mova works like this. You go from committed R1CS to committed relaxed R1CS. Then you want to fold another thing that's in committed relaxed R1CS, but the points, the evaluation points of the MLEs are different. So you reduce them to the same point. And then in the end you use essentially Nova, but apply to MLE evaluation instead of just the commitments. So this is the reduction of knowledge I've been talking about, where you just extend by saying the error is 0, and so the evaluation at the random point is 0. Then this is the point where you use point versus line to reduce the evaluations of the MLEs at different points to evaluations at the same point. And in the end, this is Nova adapted to MLE evaluations instead of commitments, which is extremely lightweight and cheap, essentially. So all in all, what you get is an extremely lean protocol to folding R1CS instances, where you have 3 rounds of interactions. So the 3 rounds come from the random challenge here, the random challenge here, and the random challenge in Nova. And you do around 12m plus 3n multiplications, where n is the number of non-zero entries in the matrices. And just like to give a bit of comparison, here are like some numbers with respect to Nova and Hypernova. So with Hypernova, the comparison in terms of prover work is similar, but you have to remember that Hypernova has this problem where it has a high number of rounds, where when you want to instantiate IBC, you run into some issue. So before you had 2 choices before Mova. Either you chose Nova for essentially its lightweight verifier, but you had like a slow proving, or you chose Hypernova for its efficient proving, but you had some problems when instantiating IBC. And now Mova is kind of like the best of the both worlds, where it's more efficient than any of them, but at the same time it has only 3 rounds. And so you can see here, like sometimes the comparison is like more advantageous than others, but essentially that's how they compare with Nova and Hypernova. Okay, yeah, so thanks for listening. If you want to read more, here's the QR code to the ePrint, and here's the QR code for our
Test.
I think we should say.
Do we have any questions? Yes.
I can just shout, otherwise it's. So with Mova you can build that IDC very easy. Like, does it also generalize to PCD like construction? Do you need to adapt things a little bit more?
No, no, because so I showed the example where you fold from committed R1CS to committed relaxed R1CS, but it works just as well for committed relaxed R1CS to itself. So you can have a tree and like you can accumulate in a DAG-based way. So you can instantiate PCD just as well.
I see. And are your constraint gates that's more complicated with the sumcheck or something like that?
I mean, we have ideas to generalize it to higher degree gates as well. There might be a way where we can take, for example, Protostar and apply some similar ideas and get a very lean Protostar protocol, which would allow us to do the same for high degree gates as well.
Thank you.
Yeah, thank you.
You have an implementation?
Yes, sorry, I realized I didn't put the QR code for that, but we do have an implementation. It's in the paper, so if you want to go check that out, yeah, you can absolutely play around with it. It's based on fortunately, like the Hypernova implementation is not very optimized because there have been a lot of optimizations regarding sumchecks lately. I don't know if you've been following that, but these are not implemented yet. So the only thing that's really optimized is Mova. Thank you.
Okay. Then again, big thank you for the